Now we are all done with the similarity criterions, in which we have seen the relationship in between the corresponding ratios or the angles of the two triangles. So is there any relationship which is related with the ratio of the corresponding areas and the ratio of the corresponding sides? So let's just see that kind of relationship under the new topic, which is nothing but called as the areas of the similar triangle. So let's just see a theorem which is related with it, which says that the ratio of the areas of the two similar triangles is equal to the square of the ratio of their corresponding sides. What does it mean? Let us suppose if I am just taking any two particular triangles. Let us suppose if I am starting the proof of this theorem, and I'm just taking the two triangles as nothing but A, B, C, and I'm just taking a triangle which is nothing but P, Q, R. Let us suppose this is another triangle which is nothing but P, Q, and R. So let us suppose if I'm writing the given is two triangles A, B, C, and P, Q, R, such that it is already given to us that they are similar to each other, because we are talking about the two similar triangles. So the ABC triangle is similar to the triangle PQR. Let's just talk about to prove. We just have to prove that the area of the triangle ABC by the area of the triangle PQR is nothing but is equal to AB by PQ whole square, which is equal to AC by PR whole square, which is equal to BC by QR whole square. This is the relationship that we just wanted to prove, that the area of the two similar triangle is equal to the square of the ratio of their corresponding sides. Now let's just talk about a little bit of construction. Let us suppose we are taking a construction over here, and I'm just drawing a perpendicular over here as nothing but AD. Let us suppose, and I'm taking this perpendicular as nothing but PM. So we are doing a construction. Draw AD perpendicular to BC and PM perpendicular to QR. So we are doing this construction. Let's just start the proof of this. So we are starting with the proof of this. So first of all, as we can see over here, the two triangles are similar to each other. So since the two triangles are similar to each other, since the two triangles are similar to each other, what can we say further? Since the two triangles are similar to each other, we can say that AB by PQ is nothing but is equal to AC by PR, which is nothing but is equal to BC by QR. We know about this fact. If the two triangles are similar to each other, then their corresponding ratios are equal. Let us suppose if I am calling this as nothing but the equation number 1. Let us suppose if I am calling it as equation number 1. Now moving on further and talking about the area. Since we know that the area of the triangle is a half into base into height. Let us suppose if I am talking about the area of the triangle ABC, it is nothing but half into base is nothing but BC, and height is nothing but AD. So hence further we can write the area of the triangle PQR as nothing but half into base is QR, and height is nothing but PM. So let's just divide these two all together. So we have area of the triangle ABC divided by the area of the triangle PQR, which would be nothing but half into BC into AD divided by half into QR into PM. So we can see over here half and half get cancelled with each other, and we are actually getting the two ratios over here. So let us suppose if I'm starting with the ratios as area of the triangle ABC by the area of the triangle PQR is nothing but is equal to BC by BC by QR, and let us suppose if I am writing it as in such a manner, AD by PM. So this is actually given to us that their ratio are actually is equal to the areas. Now let us suppose if I am further talking about the two triangles over here. So let us suppose if I am just talking about the two triangles, that in triangle ABD and the triangle PQM. Let us suppose if I am just talking about these two triangles, only these two triangles, and I am just taking this as nothing but the equation number 2. Let us suppose if I am taking this as equation number 2. So further we can say that in the triangle ABD and the triangle PQM, we can see over here that this angle is equal to this angle, since angle B is equal to the angle Q, because of the two triangles are similar. We can write it over here, since ABC is similar to the triangle PQR, so their corresponding angle are equal, and further angle D is equal to the angle M because each are 90 degree. So it implies that the triangle ABD is similar to the triangle PQR by angle similarity criterion. We can say these two triangles are similar to each other, and further if these two triangles are similar to each other, it means that what we can say about this, if they are similar to each other, then we can write the ratio as AB by PQ, which is nothing but is equal to AD by PM. We can write this thing, because if the two triangles are similar to each other, then the ratio of their corresponding sides should also be equal. Now let us suppose if I am calling it as the third equation. Now further if I am talking about the two triangles, and since again we know that the triangle ABC is similar to the triangle PQR, since we know this thing, it implies that their corresponding sides ratio means from the equation number 1. So from equation number 1 we know that AB by PQ is equal to AC by PR, which is equal to BC by QR, and now we can write it as nothing but AD by PM. So we can write from equation number 1 and 3, if AB by PQ is equal to AD by PM, we can write AB by PQ as nothing but AD by PM. So now we can again further use this particular statement. As you can see over here, if we are getting all these corresponding ratios equal to each other, so from these we are getting this ratio as well, means that BC by QR is equal to AD by PM. So if we are getting this particular ratio, so we can use this ratio in the equation number 2. So we can say from the equation number 4 and 2, we can say this: the area of the triangle ABC divided by the area of the triangle PQR is equal to BC by QR into, in place of AD by PM, we can write BC by QR. So this is into BC by QR. So again we can write it as area of the triangle ABC divided by area of the triangle PQR is equal to BC by QR's whole square. So this is the first thing that we have proved, that area of the triangle ABC by area of the triangle PQR is equal to BC by QR's whole square. So this is the thing that we have proved, and in the similar way we can prove that it is also equal to the square of this side and the square of this one. So let us suppose if I am writing it over here, that similarly we can prove that the area of the triangle ABC by the area of the triangle PQR is equal to AB by PQ whole square, and further this would be is equal to AC by PR whole square. So hence at the end we can prove that the area of the triangle ABC by the area of the triangle PQR is equal to AB by PQ's whole square, which is equal to AC by PR's whole square, which is equal to BC by QR whole square. And this is the thing that we wanted to prove, that if we have the two triangles similar to each other, then the ratio of the areas of the two triangles is equal to the square of the ratio of their corresponding sides. So this is all about the theorem of the areas of the similar triangle.